It is my pleasure to introduce Shelby Stanhope from US Air Force Academy, presenting on computer visualization and 3D printing using CalcPlot3D.
All right. Thank you, Gavin. So good afternoon, everyone. Thanks for joining in on this Sunday afternoon. As Gavin mentioned, I'm Shelby Stanhope. I'm at the Air Force Academy. I've been there for the last 7 years and have done some really fun and exciting things involving computer visualization and 3D printing using an applet that's called CalcPlot3D. And so that is what I look forward to speaking to you about today. To get started, I want to acknowledge the collaborators that I've done this work with. So Paul Seeberger is actually the creator of CalcPlot3D, which we'll become familiar with through this talk, as well as he created the direction field applet that I'll be speaking about as well. So Paul, myself, and Demore Russo from the University of Oklahoma have, over the past 3 years, been working on executing an NSF grant called CalcPlot3D in the next dimensions. Essentially, the purpose of this grant was to make all of the objects that you could graph in CalcPlot3D 3D printable. So I'll speak a bit about that as we go along. And I also want to acknowledge our close collaborator, Stepan Paul from NC State. He is actually joining us for our next grant proposal, in which we plan to collaborate with other institutions to enact change in the way they teach multivariable calculus with the use of CalcPlot3D, and also to advance the features in vector calculus. So that's my team. We have a lot of fun doing this stuff. We try to offer a lot of workshops every year on visualization and 3D printing. So that's the main things I'm going to be speaking about today. If you ever have the need to visualize in 3 dimensions, CalcPlot3D is an excellent resource for that. And if you ever find yourself wanting to incorporate 3D printed models into your teaching or your research, CalcPlot3D has opportunities to allow for that as well. So for those who have never heard of CalcPlot3D, it is a web-based graphing applet. It is free. So being web-based, you just visit the website listed below, and you can, there's the QR code posted for that as well. And that's one of the really nice things for students is that they don't have to download anything to their computers. They can use it on a cell phone, a tablet, or a laptop or desktop. In my experience, it's better on a tablet or a laptop because the phone's screen is a little bit small, but it does work on phones as well. So one of the wonderful things about CalcPlot3D is that it's easy for students and instructors to use it because it is code syntax free in the sense that it's a menu-driven application. So there are drop-down boxes, check boxes, fill in the text box, etc., that you use for graphing within the program. And I'll actually do a live demonstration here in just a moment so you can actually get a feel for that yourself. So I use this primarily for the teaching of multivariable calculus, but it can be used in any application that requires 3-dimensional visualization. So for those unfamiliar with 3D printing, the magical file that you want to get your hands on if you're going to 3D print is called an STL file. This is the file you would want to take to your makerspace or your friend who knows how to 3D print to get started. So CalcPlot3D has built-in capabilities to create STL files, and I'll preview that as well. I just want to take a moment to acknowledge some of the differences between CalcPlot3D and other free 3-dimensional graphers. So for example, some commonly known ones are the Desmos 3D graphing applet and GeoGebra. So one of the primary differences is that CalcPlot3D has built-in features specifically for the teaching and learning of multivariable calculus. So for example, any one of these graphs, you may be able to create an applet for within GeoGebra, but you may find yourself sinking a lot of time into creating that demonstration. Whereas in CalcPlot3D, there are just a series of checkboxes and drop-down lists to select in order to create these powerful visualizations very quickly. Desmos 3D also has no STL file capabilities, and they're more limited in GeoGebra. So CalcPlot3D is a better program for 3D printing as well. Okay, so off to a live demonstration in CalcPlot3D. I just want to give you a feel for what it's like to use it for visualization. So within CalcPlot3D, this is the screen that you'll see that'll welcome you to the applet whenever you visit. The primary place to get started is in this Add to Graph drop-down list. So if I click this button, you'll be able to see the different types of graphical objects you can visualize in CalcPlot3D. So we have functions of two variables that visualize the surface, space curves, vector fields. You can add points, vectors, and text labels to any of these objects that you create. It can graph implicit and parametric surfaces as well, which lends a lot of flexibility to the three-dimensional objects that you can visualize. So I would like to get started by just showing how to graph a function of two variables. So that's already pictured here. You see that this text box provides the opportunity for you to enter whichever graphical objects you want to visualize. And then it has a nice text display so that students and faculty can easily check to see if what they've entered is really the function that they were intending to. And then you can graph the object. So maybe I'll change this to a parabolate or something. So here is the object I've chosen to graph. You can zoom in and out very easily with the buttons up here. There's actually an opportunity to use 3D glasses with CalcPlot3D. If you click this button here, it puts it into a mode where 3D glasses would make it appear three-dimensional. And so this provides a nice exploratory playground for students who want to start visualizing three-dimensional space, right? There's not a lot of hurdles to jump over in order to obtain these graphs. So we hope that students can use this to investigate 3D objects and explore without getting stuck into the weeds of coding syntax. Is it a square bracket or a curved bracket? Did I miss a comma? Those type of things aren't impeding students from getting started with visualizing. I'll quickly, for those who are interested in multivariable calculus, show you a few options here for additional graphs you can create quite quickly. So as I see this button down here, it kind of looks like a contour plot. If I click it, I can create a contour plot. Here I have the option to control all of the settings within the plot as far as the lowest elevation where the contours will begin, the step size between, and how many contours I want to view. You can also edit this list directly, adding in a contour at the elevation of your choosing. So once I create this plot, we see the contour plot there. And once you click on this contour plot, it actually visualizes it in 3D with the contours right on the plot. So I didn't have to do much to create this visualization. Some of the other things I like to do in multivariable calculus teaching is add other pointwise properties to this graph. So I'm going to create this graph again. Just create the plot. You have to do this to get it back into 2 dimensions. And then I'm going to add a point up here somewhere in the plot. And it created this opportunity to add all of these pointwise properties to the graph. So I can show the tangent plane to the surface. In this particular graph, it would be interesting to look at the gradient vector. And so here we have the gradient. We can click on this point and drag it around and see that its magnitude becomes small at places where the surface is not steep and becomes larger at steep points. We can see that it is perpendicular to level curves. And so this was just meant to illustrate some of the powerful demonstrations that are easy to obtain within this program. So I will go ahead and show another object. So I'm going to just X this out and let's view space curves. So here we go into the space curve for function. An example is always provided just to get you started and have something to look at, but you go into the text box and enter whichever example you want to look at. For space curves, the really exciting visualizations provided here can be accessed in the curve settings. As you can see, a bunch of checkboxes that allow me to visualize different things along this curve. So I think I took an entire afternoon once several years ago making a GeoGebra applet that does exactly what I'm going to show here. I'm going to select the trace point and the trace vector, and there's this slider that's already there. I didn't have to create it, but as I see now, as I animate this vector along the curve, as the value of t changes, we see the position vector tracing out the curve. Okay, so again, just a couple of check boxes to obtain that visualization. Now we can have a conversation with students about the relationship between this vector valued equation and why its graph might be a curve. I'll move on to showing a bit about vector fields. So I'll show this vector field here. This is a two-dimensional vector field because the z component is 0. You, of course, can replace that with whatever vector field you wish to visualize. I'll go ahead and restrict this view to 2 dimensions with this checkbox so that we can see it here. If you click anywhere on this vector field, right now we're visualizing the flow line. You can instead visualize the curl or the divergence as well. But especially for the teaching of differential equations, there's some nice opportunities within CalcPlot3D. For example, I see a checkbox here that says show system of differential equation notation. When I check this, we're going to see the m, n, and p change to derivatives, dx dt, dy dt, dz dt. So now we can use this to visualize phase planes or differential equations. We can again, show different flow lines. And I don't know, I see some of the vectors here overlapping themselves. We can use a fixed length for all the vectors if we wish, or we can also divide by a larger factor to maybe clean up the picture as well. We can also control how many vectors we're seeing in this plane of view as well. So that's a really brief but hopefully exciting introduction to CalcPlot3D and how it can be used to visualize in 3 dimensions and be used as well in differential equations courses. Speaking a bit about the use of visualization, in my classrooms, the instructor use is to create graphs during class, to use the built-in features to facilitate classroom discussions of the concepts. You can share pre-made links or scripts with students and colleagues. That's maybe something I'll show really quickly. Just quickly going back to CalcPlot3D. Let's say I've created this visual that I really love and I want to pull it up or share it with a colleague or a student without having to recreate it. How I do that is I go up here into the file, create or encode view in the URL. This creates an extremely long URL that I can hyperlink in an assignment, PDF, Word, or share as a hyperlink with my students that will take them exactly to this graph that I've created as a starting point. And once they load it up, it'll show up exactly like this, and they can interact with the graph that I've shared with them. So that is how to share a URL. I'll quickly say how to share what's called a script. So script is a series of visualizations in CalcPlot3D. So for example, I'll look at some of these explorations, or actually, in these explorations, maybe the Lagrange multiplier. This is what a script looks like. It is a series of steps. So in this step, we have a hiker hiking along a mountainside, because the topic is Lagrange multipliers, and we're going to talk about constrained optimization. As you can see, you can add some text to this discussion and have a series of graphs that your students might go through in order to do an activity or a discussion in class. So these are called scripts, and there are links on our project website in how to get started in doing this. But I just wanted to point out this opportunity quickly. As far as students, I hope that students can use CalcPlot3D as a discovery playground where they can get in and start graphing. They can understand concepts geometrically, gain some intuition before solving a problem, or perhaps verify their answer after doing some computations by hand. So those are the opportunities with visualization in CalcPlot3D. I'd like to talk a bit about another applet that Paul has created called the Direction Field Explorer applet. So from this QR code, it takes you to an applet that looks visually a lot like CalcPlot3D from the start. I guess this green bar kind of makes them look quite similar, but this is kind of the opening screen. This is a direction field explorer. So this I use in my teaching of differential equations when we talk about slope fields or direction fields. So here we have the opportunity to define a dependent and independent variable for our differential equation. Again, just like CalcPlot3D, it has this fill in the text box style. So here you could enter an equation. Maybe I'm working with autonomous differential equation, y squared minus 1. Click enter, and we see the direction field has changed. Clicking along, I can view the specific solution for any initial condition. And I can even add multiple flow lines if I want by clicking this checkbox down here. Maybe we want to get a full picture of what's going on in this family of solutions. Another cool thing about this direction field app, I could see this opportunity here to enter a general solution. You may or may not have noticed when I changed the differential equation here, nothing changed in this box below. So it's not solving the differential equation for students, but if the students use some type of method to find the solution, they can input that solution here themselves and see it visualized with the direction field. So now they can, slide this around for different values of C and visually verify that the solution they computed here is in line with what the direction field, the slope field, would tell us the solution curve should look like. So this could allow students to see that connection between their answer and the direction field. So that's about all I'm going to say on the Direction Field Explorer app, but there's some other nice features to use this for the teaching of differential equations. Okay, so I'll spend the rest of the time in this talk speaking about 3D printing. So CalcPlot3D can be used to generate the STL files, which I mentioned before, kind of the magical necessary files for 3D printing. It can create the STL files for surfaces, solids. It can make dual colored contour plots, curves, and surfaces of revolutions, which may be particularly interesting for those teaching. Often it's covered in a Calc 2 course. So here's some of the examples of the things I've printed in the recent years in my class. So I'll quickly go to CalcPlot3D and show you how to create STL files in CalcPlot3D. So I'll just refresh here. Oh, sorry, I had opened the script in that one. Okay, once you've entered CalcPlot3D, nearly everything in the program is 3D printable at this point. So let's say that this is the object I want to create an STL file for 3D printing. It's helpful to increase the number of grid lines to make this a little bit smoother of a print. So maybe I'll go up to 50 or something. And now I go up here into the file and simply select create an STL file from the plot. So really, once you're happy with your visualization, the next step of getting an STL file for that object is as simple as this. So after clicking that button, I see some opportunities to change some settings before I save the file. So this is just the name of the file that it will save as in your downloads folder. This next set of options allows you to select a relative dimension to thickness ratio. Certainly, you can change this sizing before you get the file into the 3D printer, but this gives you some kind of relationship between the size of the object and the thickness of the object. Typically, so it's set to a 4x4 inch by default because the default screen in CalcPlot3D goes from -2 to 2. So like an inch corresponds to one of those tick marks. If the object is closed, like a sphere, then you don't need to add thickness to it. And you shouldn't, in fact. But when the object is not closed, like this paper-thin surface that we're viewing here, you must add thickness in order to 3D print this object. Okay, so to add thickness, you have some different options in the direction in which to create the thickness. And if you float your cursor over each of these, it will describe how that thickness is created. So opposite normals says it's going to create a thickness typically below the surface. So this maintains the mathematical precision of the top of the surface and will deform the bottom by creating a thickness below the surface. We can do it opposite normals, which is typically above the surface, half and half, which is helpful. For example, if you're creating a Mobius strip and you want it to come together flush, you would want to use half and half. Or the Z shift down option takes the object and shifts all of it down in the Z direction. This could be dangerous for steep areas of the curve because a Z shift down won't create much thickness. So I'll just click opposite normals here and we can view the solid to see how the thickness plays in. So this is where you need to be a little bit careful about how many grid lines you add. I would put it up to 50. You know, don't go crazy there. If you did like 1500, it would take a while for this solid to be created. So as we can see in the graph here, there's a thickness now in this paper-thin surface, and creating the file will download that STL file to your downloads folder. All right, so I have been using 3D printing in my classroom for, I guess, the last 6 years now up to this point, and it has been a really lovely experience. For those who haven't 3D printed before, don't feel intimidated. I had never even seen a 3D printer prior to 2019 and was printing away within a month. So usually you can find someone who likes 3D printing and they'll be excited to tell you all about it. I also use a process called thermoforming, which is where you 3D print a solid buck and melt plastic over the top of it. The great advantage to doing this is that you can mass produce much more quickly than 3D printing. So I'll just give a quick preview of how I've used 3D printed models in my classroom. And this was in the teaching and learning of multivariable calculus. So we created a set of mountainous surfaces for our students to explore because I wanted to create a set of surfaces that could be used in multiple different activities, not just a one activity or one topic object. So we use them to develop the idea of contour plots. Students are drawing on these surfaces after I've added a whiteboard marker-friendly sealant to the top of the 3D model. They're able to write on it with whiteboard markers. They can use the 3D objects in conjunction with visualization to learn the concepts of the course. We take students out to a hill out on campus and walk around to introduce partial derivatives, and then use the models to have students identify different locations with various partial derivative properties. And we also have a Lagrange multiplier activity for constraint optimization that goes with that script I showed briefly earlier. And that script is available to anyone who wants to use it. As you can see, I accessed it in the file in the explorations. Also created an activity using 3D printed models where students in small groups are given this kit of models and this tabletop axes system. along with a worksheet with a whole list of fully set up triple and double integrals. Their objective is to match the object with the integral that computes its volume. And this was developed in collaboration with a student as well. So here is our project website. I just wanted to point out a few opportunities that are available there. So here's a link to the direction field applet as well as CalcPlot3D. There's a CalcPlot3D intro video to help you get started in visualizing using that applet. We have an STL creation file tutorial, that's a PDF as well as video to help people get started. We also share, we really feel that we want to share everything we've developed with people out there and let them take it, modify it, do what they want for their classroom. So all of the 3D printed learning activities are available as well. So here's again all the QR codes to CalcPlot3D, the direction field website, and our project website. And I just thank you for your attention and be happy to take a few questions in the remaining time.